Hello everyone and welcome to helpyourmath.com. In today's video we're going to be covering the infinite limit process and Riemann sums. Now this is really important because when you're doing a Riemann sum you're using these formulas for constants, the i's, the I squareds, the I cubes, which are not listed, but particularly it's really important on how you handle your processes for these infinite limits. So here what we're going to do is we're going to separate the actual problem, take away the delta x, and we're just going to deal with the function that deals with an n and a constant, an I with an n squared and a constant, then we have the I squared with an n cubed and a constant. So our first step still remains the same. The first thing we want to do when we see this problem is separate the function. Right, so here we have the summation, here we have the n, I is equivalent to 1, and we have 3 over n. So what we want to do is get the n out of this. So we're going to factor it out and pull it in front of the limit. Right, so we have the limit as n approaches infinity, we have 1 over n, summation, as I goes from 1 to n, and here we just have that constant now. So now that we have the n separated from everything, we can finish this later after we take the limit, but first, let's use the constant rule, right? And here we have the rules for the Riemann properties of the summation, right? So here we're looking at the first summation rule. Whenever we have a constant, we take that constant and we multiply it by the upper limit, which is n. So here, and that's only if we're starting from the value of 1, right? So here we have the limit as n approaches infinity of 1 over n times, and we're going to have here in parentheses 3 times n, right? And now we can take the limit. But in this case, we see that we have, this is a numerator, right? This goes over a 1, so we're multiplying the top with the top, and we have here then the limit as n approaches infinity of 3n's over n. And now we see those n's go away. They simply divide each other out perfectly, and we're left with the limit as n approaches infinity for 3. And now we see there's no n, there's nowhere to plug in this infinity, so the solution for this is simply 3. So we're going to write that answer up here so that you guys can recollect it while you're looking at the rest of this video. Let's continue to the next one, all right? So I'm just going to wipe this down. If you need to watch this part, just rewind this a few seconds, a minute back or so, right? Let's move on to the second one. Now we have the limit as n approaches infinity for the summation as I goes from 1 to n for limits, and then we have 6i's over n squared. And this time we're going to be using the I function, but before we begin, again, let's factor out that constant and the n squared term. In the first one we didn't factor out the constant because that's all we had. We didn't have an I, but now we have an I, so we want to factor out everything except that I. So that means the 6 goes and the n squared goes. So we have the limit as n approaches infinity of 6 over n squared. And here we have the summation. Then on top, I on the bottom, and we have the term I. So now we can take the summation. So let's begin it then. So we have the limit as n approaches infinity, 6 over n squared times, and the formula for this of I is right here. We have n times n plus 1 over 2. The simplified version after distributing is n squared over 2 plus n over 2. So this will be the multiplying factor. So here we're going to put this in parentheses, and we have n squared over 2 plus n over 2. And what we want to do is distribute this term to each of them. So now we have the limit as n approaches infinity of 6 times n squared is 6n squared over n squared times 2 is 2n squared. And then the second term we have is plus 6n over 2n squared. Now realistically, when we're looking at this limit process, we know by the rules of our former days of learning the limit process, the rule for whenever the exponents are equivalent is just the quotient of the two terms. When the numerator's power is lesser than the denominator's power, we know this limit goes to 0. But how does it go to 0? This is a really good question. It's something we ought to pay attention to. When doing the limit process, we have 1 over 1. Right? Think of this. As the denominator goes to infinity, what's happening? This is 1 when we divide it. 1 over 10 gives us 0.1. 1 over 100 gives us an even smaller value. Right? 1 over 1,000, even smaller. What happens when we have 1 over a million? It gets really small. Even smaller is 1 over infinity, which is approximated to be exactly 0, right? So in this case, when we're looking at this limit, we know that this is going to go to 0, and the reason for it is the simplification looks like this. This becomes just positive 3, and here we have 3 over n. So plugging in the infinite limit in this position gives me 3 plus 3 over infinity, which gives me what we call a 0. And the solution for this is still just 3, right? All right, let's move on. Let's move on to the next term. So our second limit here, also a 3. Now to get to the next one. We have the limit as n approaches infinity for the summation as 1 approaches n for negative 5i squared over n cubed. This one's going to be a lot more work, but let's factor out that constant term with the n term again, right? Just as before. So we're going to have the limit as n approaches infinity of negative 5 over n cubed. This is multiplying by the summation as I goes from 1 to n of I squared. And in this case, what we're going to do with it is we're going to use the third formula we have here. We're going to see that we have n times 2n plus 1 times n plus 1 divided by 6, which simplifies to these 3 terms once you break it down. And so we're going to use the shortcut method to solve this component of it, right? So here we have this constant term over here, negative 5 over n cubed, times the summation formula for I squared. So here we're going to have n cubed over 3 plus n squared over 2 plus n over 6. And it's safe to assume that every other term, which I'll show you what they look like first before denying that their limit was not 0. So here we're just going to distribute each term. We have negative 5n cubed over 3n cubed minus 5n squared over 2n squared cubed minus 5n over 6n cubed. And it's safe to assume these with the greater denominator powers are going to go to a 0. So we can neglect them and only focus on the leading term here. Now by looking at only the leading term, we see the exponents are the same. We get rid of those exponents as we plug in the limit. Our solution, negative 5 over 3. And that's the limit process for infinite limits. Thank you. Now finally, to recap the whole idea of what we're doing here is we want to neglect the terms that we don't need to use. So when you're looking at the formula, always remember that the leading term is the only term you have to worry about. The reason for it is the power that you're going to have on the leading term will always match the power of your denominator in infinite limits when you're doing Riemann sums. Now what's going to be neglected is every other term. See, we have this other parts of the formula, but we don't really need it. What we do need is just the leading term of every piece. The same was seen in the last one that we did. In the last one, we also had a second term that was neglectable because it goes to 0 anyway. The denominator power is going to be reduced. As we see, the leading term is n squared, the second term is n. This will always create zeros, just like these two did. And for that reason, we want to neglect everything. So if we're looking at this in a different light and we say, well, what's going to happen with the limit process? Well, I know these are going to go to 0. So technically, I don't need them. So when I'm loading up my limit and I have the formula for the summation, the only thing I want to pay attention to is that leading term and the coefficient of the leading term. So if I have 2, or rather n, times 2n plus 1 times n plus 1 over 6, the only thing I need to be concerned with is this times this times this, the leading term over this. And so I'd have the limit as n approaches infinity of negative 5 over n cubed, multiplying solely on the multiplication of these 3 leading terms over this denominator. So I have n times 2n times n is 2n cubed over 6. And this is going to create the actual solution for my limit process. Everything else is just going to go away. The n cubed with the n cubed. The 2 and the 6 make 3. And there's my solution, negative 5 over 3.